In the last lecture, we saw how to create finite automata given from a given regular expression. Right. For example, here this regular expression is given, and we constructed this, and this construction in fact proves the theorem that given any regular expression, the language that it denotes is actually a regular language because it is accepted by some finite automata, right? Now, from here, the other direction is not clear, right? So the other direction means given any regular language or given any finite automata accepting that language, we should be able to construct some regular expression which denotes the same language. Now, this part is not that trivial to see because regular expressions are only allowed to have these operators, this plus and some concatenation, which we have not shown as operator, but there is some concatenation at play, and then this clean star, right? So the question is, can we construct any regular language with the combination of these operators starting from this singleton set? So this is a singleton set, this is a singleton set. We are also allowed to have epsilon, so as a set, right, and phi. So as regular expressions they are. So we defined this, right? Yeah. So we defined this. So these are singleton sets, and these are our ways to construct more and more complex regular sets. So now the question is, can we construct any regular language using just this operator? So this is not so obvious because you see, any regular language means we are talking about any arbitrary finite automata. So since we have already proved that it is equivalent to some DFA, deterministic finite automata, and deterministic finite automata are simpler to tackle. So, but even if we are considering deterministic finite automata, it can be anything, any directed graph. It may not be such that we can break it up into this concatenated with this and then this sort of thing. So it can be a very complicated looking graph. Now, how can we just cast that thing as some combination of union and concatenation and clean closure? So that is the question, right? So first of all, we will define this set for any given automata. So consider DFA. Okay, so this thing is a DFA. This is important that this is a DFA, and suppose L is regular and L is accepted by this DFA M, right? So L is accepted by M, and we also assume that the transition function is total. That we can also assume because we discussed about that dead state and all those things, right? So if you forgot, you just revise that part about dead state. And here just something to notice that we have used our start state as Q1, and we have n many states, Q1 up to Qn. So this is how we label our states. It's just some labeling. We have to give some name. So this convention will help in writing the equations cleanly. Okay. So now consider integers between 1 and n, right? So ijk's are integers between 1 and n, and parameterized by this integers. We define this set R sub ij super k. So this is the set of strings which correspond to a path from qi to qj with this additional constraint. Okay. So first of all, this part should be clear. So that means w is here. If you start from qi and process this w, then you should end up in qj. So the path looks like this. You start from qi and then you process all these symbols of w. So suppose there are t symbols, and then you end up in qj. So this is one condition, and so this has to be true, and you must also satisfy this condition, that is the index of any intermediate nodes, and by index I means just this. So the index of state qi is I. So you remember that the states are q1 up to qn. So if you take any qi, okay, so the index of qi is I. Okay, so this is saying that if you take any proper prefix of x, right? So your by proper prefix means it's a prefix and it's not epsilon or w itself. So you have a w here. A proper prefix means something from this initial part up to some, say, a k, and by initial part I mean that it cannot be just this empty string here, or it cannot be the entire string. Okay, it has to be strictly in the middle somewhere. So this part, you can say that this part is Rx, right, for this W. So okay, so X is say somewhere here. If that is the case, then you consider the state that you reach after processing X. That means you consider some intermediate state. So excluding X from these two possibilities means that this thing, this hat of Qix is not this or this, because this will correspond to X being epsilon, this will correspond to X being W. So we are excluding those. We are considering any intermediate state, right? And we are saying that for all intermediate state, so if QL is an intermediate state, then this L is less than equal to K, right? K is an integer. So that means the index of all these intermediate states are less than equal to K. So this is what it means. So just absorb this definition. This will be important. Okay. So you got that? You consider all the strings which starting from Qi can lead you to Qj, but not all that kind of string, a subset of that string which also satisfies this condition that when you are going through this path, all the intermediate states, index of the intermediate states are less than equal to K. And since we have a DFA, and we have a total function, so there is always a path, always a unique path, right? Given Qi and W, there is a unique path from Qi, and that path doesn't get stuck because this is total. So you consider the unique path, and that path should have this property. So only then you include W here. Now you see, by definition, this Rij k minus 1 will be a subset of this. Why? Because what is this superscripted parameter saying? That all the intermediate states are of index less than equal to k. So if it is less than equal to if it is less than equal to k minus 1, so then it is automatically satisfied that it is less than equal to k, right? And the initial state and final state, these two states are same here, Ij. So here are all the strings for which the path doesn't contain any intermediate state with this index more than k minus 1. Here it doesn't contain anything more than k. So this is trivially a subset of this one. Okay. So but this can be a strict superset, right? Because here you are only allowed to have intermediate states up to qk minus 1, but not k, right? But here you can have up to k. So here you can have extra more strings than this, which uses a path going through some qk, right? So what are those strings? So now we consider those kind of string that which are here but which is not here. So this this minus this thing. Now see if this is the case. Okay. So then what can happen is the path for w, okay, from qi to qj. Okay, it must pass through qk at least once, right? Because we are excluding this set. So all that is here, it must pass through qk, right? At least once. So this thing looks like this. Okay, so it starts from qi, right? So it is going through the intermediate states, which are sorry, this should be qk, so there's a typo. There's a typo here. So there's a typo, please so yeah, for this w, you process the symbols of w, and so far you haven't encountered qk, and at some point of time you encountered qk for the first time. Say you have already processed this y1, which is a prefix of w, right? So these are strings, these are not symbols. So this is all these yi's are strings. Okay, so you yeah, you are processing this w, and after you have processed this y1 part, you encounter qk for the first time. Okay, so then you may encounter qk again. So again you go through some path which doesn't have qk, and all the things, all the intermediate states, sorry, here. Is this stupid thing happening? So all the states say here. So these states are also so these states are also of index less than k, right? So here also all the intermediate states are of index less than k. You encounter k, and then again you take some path, and you may come back to qk, or you can say encounter qk just once or take this thing, but in general what can happen, you go here and then say you encounter again k, again qk, again qk. So if you are encountering this qk say some t many times, so that means you have some t minus 1 many strings here. Okay, so you encounter this, some take some path, again come back here, take some path, and all these paths, right? So there in here all the indices are so here all the indices are less than equal to k minus 1, right? Because we are explicitly marking this qk here. So everything else is of index at most k minus 1, right? So if that is the case, then you see that this y1, this part, this should be in this set, right? Why? Because it starts from qi, it ends in qk, and the intermediate states are of index at most k minus 1. Similarly, this yt should be in rkj, that means it starts from qk and ends in qj, and all the intermediate states again are of index at most k minus 1, right? And similarly here also it starts from qk, comes back to qk, and the intermediate states are of index at most k minus 1. So all this y2 to yt minus 1, so that will be rkk k minus 1, right? So any string here should be in this set, right? So this is the concatenation of this with clean star of this with this thing, right? We have a clean star here because what does clean star means? You can have any number of strings from this set and have a concatenation of that, right? So that is what clean star means. So this multiple path here, so this is captured by this whole thing star, and this is captured here, and this is captured here. So this w will be here, and this is so we have proved this direction from here to here, and the other direction is also true if you go from here to here, because if it is here, then you can break it down into this format, where this y1 is here, yt is here. So all the steps you can reverse, right? And if this y1 is here, then you can have a path which doesn't have any anything. So all the indices are less than equal to k minus 1 for this. You just reverse the argument. For this yt, all the indices are, so all the intermediate indices are at most k minus 1, and so from here you can also see that this will be in this set. So it's an if and only if condition. So since it's a if and only if condition, so this equality holds, right? So this set is precisely this set. Okay. Now once we have this and this, so this is part of this, and if we remove this thing, the rest is this. So what is this then? So it's just the union of this two things, the union of this and the union of this, which we removed from this. So if we take a union, so then this is what we have. So this is the most important identity, so that we need, where the definition of Rijk is this. Okay. So just make sure that you understood the derivation of this identity from here before going to the next slide. Okay, so if you are fine so far, then let's move on. now see, this equation gives us a recursive way of defining this R ijk, because you see this k is bigger than k minus 1, and so this thing is being described as some combination of some simpler things. By simpler I means this parameter is less than this parameter. So all these things, this k minus 1s can be expressed in terms of k minus 2, k minus 2 can be expressed in terms of k minus 3, and so on. So the base case which you have to figure out is for k equal to 0, right? Okay, so we have said that k belongs to this, so we can in fact for k we can say that k actually comes from not 1 to n, but say 0 to n. Okay, so we include also 0 for the domain of k. Okay, so now what are the strings in Rijk? So these are precisely the strings which lead you from qi to qj, and it does not pass through any intermediate with index more than k, right? So the index can be at most, k. So all such strings constitute this set by definition, right? Now what does it mean to set k equals 0, right? That means here you can't even have q1, you can't have q2, so you cannot have these states as intermediate states, but your state starts from q1, right? So this means that you cannot have any intermediate state at all, so you cannot have any state here, right? So then how does this path looks like? Okay, so one case is that it's just a direct transition, okay, like this. So it's just a direct transition on a single symbol, right? So here you have just a single symbol. So this symbol itself is your w. So your w here is just a symbol. Okay. So you have this. Another possibility is that this path is of actually 0 length. Okay. And 0 length means this qi and qj are same. So j is equal to I, and then what string are we talking here about? So it's an empty string, right? Since we are talking about DFA, you see that there is no epsilon transition, right? So in DFA, by the definition of this hat, you can only have this q hat qi going to qi with this empty string, or you can have this thing like this. So here also you can have qi equal to qj, but for that your DFA, so say this is your qi, and you can have an arrow back here, right? So you can have this thing. So this falls into this category, though we have shown this to different circle. So this I can be equal to j, I may not be equal to j. So here both possibilities are there, but here it is a transition on a single symbol. But here there is no transition at all. So this path is of 0 length, and so that is why this I is equal to j, and this is epsilon. Okay. So is that clear? So here I can be equal to j, but it may not be equal to j. but in any case you have to have a single transition, either of this sort or this sort, labeled by a symbol. Here there is no transition at all. So this is what defines the case for Rij 0. So you see, if I equal to j, then you can have this sort of transition. So it's going from qi to qi, but I equal to j. And it can also have epsilon, right? And here you can also have a transition on single symbol, but you cannot have epsilon here, because if these two are different, you cannot have a epsilon transition because we have a DFA, right? So here there is no question of epsilon. Here you always have this epsilon, okay? For I equal to j, you always have this epsilon, and on top of that, if you have a loop like this, then you have something from this component also, right? So this defines the sets for k equal to 0, and once we have this for all ij, we can define it for k equal to 1 for all ij, then k equal to 2 for all ij, okay? So what else do we have? See, when is a string accepted? Say by this automata. So first of all, see, if we want to lift this restriction, okay, if we want to consider the strings which satisfy only this condition, so then we can set this thing as n, right? Because we only have states up to qn. So whatever path we have, I mean, it doesn't contain anything beyond n, right? The index doesn't go beyond n. So if we put n here, so that's like I'm removing this constraint altogether, right? So that means you can go from qi to qj by processing w if this w belongs to rij n. So putting n here means we are not caring about this condition anymore, right? So this is true for any ij, right? And what are the strings that are accepted? So a string is accepted if you start from this starting state, which is in our case q1, and you end up in some final state. So yeah. So if this qf is in f, is your set of final states, and starting from q1 you can reach this qf using w. So then this w is in your language, right? And how can you express this condition? So this we can express like this, right? So it comes from here, right? And then since you can have multiple final states, you have to take all such strings for all values of f, right? What are these f's? So this corresponds to the qf's in your set of final states, right? So this is a subset of this q. So you will have some indices corresponding to this f. So you take all such indices for the final set, and you take all these sets, and you take the union of that thing, okay? And so here it is. So you take all such states in your final state, and for all these f's you take a union, a big union of all this thing. So then that means your w is in L if and only if this is true. So that means your L is actually this union, okay? So your L is this set. Fine. So we have expressed our language, the given regular language, in terms of this set. So now, after deriving this equation, it should be absolutely clear to you. But just to finish it off properly, so this is how we do things. See, first of all, we show that we can construct regular expression for this k equal to 0, right? So in this case, we do not have any epsilon. If I is not equal to j, we can have some symbols, right? So these are not strings, these are just symbols. And for each symbol, we have a regular expression, right? So what does this mean? This means the singleton set containing A1, right? So you take the union of all this thing, and in case of regular expression, union is expressed in terms of plus, right? So you take plus of all such AIs such that that symbol satisfies this condition. That from Qi you have a single transition to Qj, right? So you take the plus of all such so any symbol here, so that must appear here, right? And then if I is equal to j, again you take all the single transitions. So since now this is equal to j, I am talking about a loop like transition from Qi to Qi itself, say on certain symbols, so A1, A2, whatever, right? So you take all such symbols again, but then on top of that you also take this epsilon. So this epsilon will also always be there if this I is equal to j, as we discussed in the previous slide. So you also include this epsilon, right? So these are your so this is your regular expression for just this set, which is just a union of symbols or union of symbol plus this and this epsilon string. Now once we have this, right, how can we express this? So again, this is now simple because sorry, we have this plus, not just this plus R I j k minus 1. Okay, so just make this correction. So we just typo, there is a typo. So so this union is captured by this plus, right? So recursively we can define this thing. So we say we have already defined this thing. So we have this, and here also it's just the same thing. Concatenation is concatenation and clean star is clean star. So these are fine. So these we can capture with regular expression, right? So this will be the regular expression in terms of the regular expression we already constructed for k minus 1, right? So if you can construct the regular expression for k minus 1, so then we can construct the regular expression for k. And after after doing everything, So here again so this should be the sum of all R1F n, right? So this is the union of all R1Fn. So corresponding regular expression will be, so again here is a typo error. Okay. So just make correction for this and this. So once you have constructed everything up to n, so you have constructed this Rn for all ij, right? So now you just take, instead of taking all ij, you just collect all this R1Fn for all this f which corresponds to this final state, and you take the sum of that. So you take plus 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 plus, right? And that will be the regular expression which denotes this L, which was the given language here, right? So that means given any regular language, we can construct a DFA accepting that language, and from that DFA we can construct a regular expression recursively using this as a base case and this as a recursive step to construct all ij k for k up to n, and then we take this thing and then take the sum, and that sum is the regular expression for this language L. Okay. So here is an example. So the language is instead of language, the DFA is given. So from this DFA, how can we construct this thing? So first we use this part to construct this R's for k equal to 0, right? And you see that if I is equal to j, then that it always have this. So you see that for 1 1 we have this, and we only have this, nothing else, because from 1 there is no self loop, right? So here there is no self loop at all. So all this 1 1 2 2 3 3, they are just epsilon. If we had something here with some symbol, then we would have that here. Then for this single transition from Q1 to Q2, we have, say, this 0 for 1 2, right? So this corresponds to this equation, that if you have a single transition, we have that here. So in fact this here as so this, and also say from Q2 to Q3, so 2 to 3, yeah, here we have 1, right? 1 to 3, 1 to 3 1, and yeah, so for all this okay, so from 3 to 2, you see we have 2 symbols here, right? From 3 to 2, so that is why from 3 to 2 we have 0 plus 1, right? So this is precisely the set of strings which can lead us from Q3 to Q2 without passing through any intermediate state. And we also have 5, so 3 1, so if you see 3 to 1, right, so there is no transition at all. Okay, you cannot go from Q3 to Q1. There is no string which can, not even epsilon or anything. So that is why this is 5. Okay. So yeah, here I should also just mention that if this set is empty, so this set cannot be empty because you always have this, but if this set is empty, then you can have phi also, right? So yeah, now for k equal to 1, we employ just this equation which comes from here, right? So I'm not doing this for each of this thing, but you can do that. So for example, say this, say r r 2 to 2, sorry, 2 to 1. R 2 to 1. So what will be this? So it will be first of all R 2 to 0 plus then you have R 2 to 0. Okay, so here it's kind of, since I have taken this to same, so here it will be, so here this is say I j and this is k. So here we have I j k minus 1, and here we should have I k, so this should be 2 1 k minus 1, then here I should have k k k minus 1, which is 1 1 0, and then this whole thing should be in clean star. Then from k to j, and then k minus 1. So this should be 0, and this should be 1, and this should be 2. It should be 1. So 2 to 0 is here, this is epsilon, right, plus 210 is what? 210 is 0, so this part is 0, and then this 110 is epsilon, so we have epsilon star, and then 120, so 120 is again 0. But you see, epsilon star is epsilon, and 0 epsilon 0 is 0 0, right? So you have epsilon plus 0 0, which is this thing. Similarly, you once you construct all these things, so from here again using this kind of formula, you construct it for this thing, and then what will be our final regular expression? So we should take R1 2, because 2 is a final state, and here we should have 3, because 3 is n, then also 3 is a final state, so we should have R1 3. So this 2 and 3 corresponds to this 2 being final state, and this here, so this is just n, right? So whatever that thing is, 1 2 anyway, so you should construct these things. So yeah, so so here we have a proof that you can construct a regular expression for given for any given regular language. So what did we do then? So we first defined deterministic finite automata, and then we defined a generalization of deterministic finite automata, which is non-deterministic finite automata without epsilon transition. So this is without epsilon transition. And by definition, it was generalization. But then we showed that we can construct a deterministic finite automata from this NFA without epsilon transition. And this was the power set construction. You remember? It was the power. It was a power set construction. So then we defined another generalization of NFA, which is NFA with epsilon transition, and then we showed that we can remove all this epsilon transition to construct a equivalent NFA without epsilon transition, right? So here we defined all that epsilon closure, and all those things. So from here to here, we somehow absorb this epsilon closures in the transitions here. And then we defined regular expression, and from here we showed a method to construct a NFA by doing this. So if you have class or concatenation, then you use this sort of so then you have some machine here, then you have this machine and this machine. So this was the direction that we used when we were proving that for any given regular expression you can construct a finite automata. So concatenation was handled by this, and then epsilon transition, and then some machine here, right? So all these machines had a unique start state and a unique final state, right? So this was the case here where we are converting this regular expression into a epsilon NFA, and then we showed that given any deterministic finite automata, so via this R, I, J, K, this thing, from here we can construct something here. So we took this path. So it shows that everything is equivalent, right? So everything is equivalent. And now we are kind of done with all the models to deal with regular languages, right? So everything here, so the language, so the language is important, not which automata you are using to recognize it. So everything here, so this just corresponds to the regular language. The regular language, right? So later we will also see something called regular grammar, but that we will discuss when we discuss grammar. So first we discuss at least context free, then we will define those things. But for now, yeah. So these are the models to deal with regular language, and that's it.